So when it comes to developing new AI applications, I argue that the biggest bottleneck today is neither capability nor compute, but trust in the infrastructure that enterprises deploy on. So advances, as most of us probably know, advances in modern AI performance have been driven very much by increasing model size, leading in turn to greater complexity of the infrastructure required to train and run foundation models. It's now the norm to have very distributed computing architecture integrating both general purpose processors and specialized accelerators like GPUs. So unfortunately, the standardization of protocols to secure those distributed architectures have really not kept pace with the system complexity. And that leaves us with a growing gap between the AI applications that we are theoretically able to implement and the AI applications that we are able to confidently secure. So this specialized distributed infrastructure required by high-performance AI, especially in public cloud environments, brings unique security challenges, and companies are still kind of grappling with these even as they continue to test new applications. So my question today is, how do we build hardware systems for AI with security and confidentiality guarantees that stakeholders can actually trust? Before I get into the potential solutions, I just want to introduce myself and explain why I wanted to speak to this community. My name is Shannon, and I lead research for a new computing venture incubated at Deep Science Ventures. So part of my work is scientific. I am designing experiments, writing papers, but another big part is just scanning different markets for opportunities and gaps where new ventures in our portfolio could address. So today I'm sharing my perspective on security innovations that I see as near-term enablers of both general AI adoption and new venture creation. And I'll focus on hardware-based approaches, namely confidential computing using existing trusted execution environment technology, or TEEs. And my goal is to provide a perspective more on the market dynamics than the technical aspects, but we will get a little bit technical. What really interested me in this field is that the core technology of TEEs is quite mature, and that makes it ripe for new ventures. But there are significant missing pieces which require input from security researchers like you. So I hope to convince you today not only that the problems in this field are very interesting technically, but that your engagement as security researchers is really essential right now to set foundational safety protocols and bring more transparency to this field. So let's start with some context on confidential computing. This has emerged as a promising framework to protect AI data and models, even as they're processed on third-party infrastructure. And I'll start by emphasizing two key ideas that we'll return to throughout. First, confidential computing is considered the most practical and scalable path to enhance security of entire AI workloads. And that's thanks, again, largely to existing CPU-based TEE technology, which is widely available in commodity hardware. On the other hand, important gaps remain with respect to bringing AI accelerators within the trust boundary, especially when more than one GPU is involved, which today is pretty much always the case. So these are the key ingredients of confidential computing which allow it to protect data in use. First, remote attestation based on cryptographically signed system measurements. Next, memory protection plus virtualization isolate a process from other software on the same physical machine, very important in public cloud. And that includes high privilege software like the OS and cloud hypervisor. And finally, the entire runtime memory is encrypted and decrypted on the fly to add that extra layer of security. And collectively, these ingredients ensure that private data and code is visible only in the desired context. But you may be wondering, like, why do we need hardware-based security features for AI applications? And my take on this is basically everyone, providers and customers, have very different constraints on where their data can be processed and what infrastructure is available to them. So the lower the level of the tech stack that these security features can operate at, the more use cases and implementations they can actually benefit. From a commercial perspective, the push to extend confidential computing from CPUs to GPUs and beyond comes from two main sources. On the demand side, data breaches are extremely costly to any company, and even more so in regulated sectors. Think healthcare, financial services, government, defense. For these companies, there are both higher legal consequences and higher consequences to society. And they basically cannot implement AI if it means possibly exposing their data to bad actors. The problem is a single entity might not even have enough data to build a useful AI application. But if different parties can collaboratively send their data and train a model without exposing private data to one another or even to a trusted third party, then they can all benefit from a more accurate model. And one use case that people in financial services are really excited about is fraud detection. Here you really benefit on accuracy from picking up on systemic trends across a larger transaction network, and that helps accurately diagnose abnormalities. On the supply side, AI companies have a huge incentive to protect their IP, which represents millions in R&D investment. But if they could run their models on external hardware with mechanisms to verify that the system is in a trusted configuration that will protect against model theft, that unlocks new business models. Ultimately, it allows them to better serve their customers, who can now use AI services on any infrastructure that suits them, including their own, so long as confidential computing or similar verifiable security features are enabled. Now, in my opinion, it's this side of the equation that's really driving the demand for trusted hardware and confidential AI. And I think pressure from this side is why hardware vendors like NVIDIA are ramping up efforts to implement confidential computing on GPUs. So the key takeaway is that organizations may be unwilling or unable to pursue certain AI applications if it means sending data and models to a third party, even if this would lead to better AI performance or even better fulfill customer needs. Without stronger guarantees around confidentiality and system integrity, many AI solutions will just be blocked altogether, and the impact that these models can have is then limited. So, given this picture of why hardware security features are in demand, let's address why confidential computing is considered the leading framework to achieve confidential AI guarantees. So it mostly boils down to technological readiness of commercial TEE implementations on CPU. And major cloud providers already offer confidential virtual machines based on this technology. Because of this maturity and the time that they've had, hardware vendors figured out how to run TEEs with minimal code changes on the application layer and also relatively low performance impact. And these factors are the most important for enterprises considering any kind of tech transition, not just AI. We hear these requirements over and over again in our customer conversations at DSV. So the remaining technical challenge is extending CPU-based TEEs to incorporate GPUs with as little additional overhead as possible. The question is, how do we go from 0 to 1 and 1 to many GPUs getting us closer to encompassing like full distributed AI workloads inside a confidential computing environment. So today, the 0 to 1 GPU case is more or less solved, albeit only in closed source. And the key technical features developed to enable this were, first and foremost, encrypted CPU to GPU data transfers, as the PCIe interconnect is generally considered untrusted. And this also necessitated the creation of a secure channel and a key agreement protocol for across the CPU-GPU boundary. Second, they needed a way to validate the secure configuration of the GPU, including firmware signing and remote attestation. Finally, new mechanisms for GPU memory protection were introduced, ensuring that protected memory regions are accessible only via a validated driver running within an attested CPU TEE. So now today's single GPU confidential computing has been demonstrated. There's excellent code compatibility, little performance impact, at least for memory constrained workloads. But one GPU is not enough for modern AI models whose weights might not even fit in the memory of a single GPU. However, there's still tons of uncertainty around how multi-GPU confidential computing will actually be implemented, and also how the cryptographic overheads evolve as the number of confidential GPU nodes scales. So in fact, in the current threat model, they assume that the on-package memory of the GPU is secure. So the high bandwidth GPU memory and GPU to GPU communication is not even encrypted. If we were to re-examine that assumption and have to establish secure channels for GPU connections, or even additional networking, these overheads could become a really big performance problem and therefore a bottleneck to commercial adoption. Finally, another point of concern for me is that NVIDIA CC is currently the only GPU confidential computing implementation that's anywhere near production ready. And because of NVIDIA's closed ecosystem, there's very little transparency around the technical details of their implementation. Security researchers have already taken note of this, and just last month, a group from IBM went and released this paper trying to look under the hood of NVIDIA CC to understand what is going on. And I think work like this is super important to facilitate broader understanding of GPU confidential computing, which might lead to researchers like you proposing useful extensions. This brings me to the final segment of my talk, where I want to take a step back and explore ecosystem-level needs to encourage industry adoption and enable more transparent confidential AI implementations. 4 focus areas I'd love to see more progress in: clear technical standards to guide development, validation frameworks to check those CC implementations against those standards, open source reference implementations that developers can both learn from and build on, and finally, more crosstalk between security and AI communities to create a shared vocabulary and more aligned goals. I think these contributions would give both established companies and startups a good template for securing their applications and help them create more useful, trustworthy AI products. Now, I've been told that security researchers don't all agree on the utility of standards, but from an industry perspective, standards and validation frameworks are extremely important to enable vendor flexibility while maintaining trust. Like, if you're a newcomer to a market like a startup and you're trying to close your first customer, being validated by a trusted and widely used framework can be extremely valuable. I'm a big fan of NIST's cryptographic module validation program, which has validated over 1,000 cryptographic modules according to standards in the FIPS 140-3 umbrella. And I'm a fan because it contributes to both increased trust in vendors and additional transparency in the field, because you can go and search up every single one of these implementations and figure out exactly what algorithms they implemented. And the NIST standards within FIPS 140-3 have been extremely useful to our venture development process, even at pre-seed stage, because their recommendations provide vocabulary that I can use to go talk to experts, evaluation tools that we can use to check if we're on the right path, and a clear path to legible proof points, which has informed our roadmap. Unfortunately for TEEs and confidential computing, we do not have that consolidated standard or validation framework yet. So the market has to default to trusting whatever NVIDIA or Intel tells them their implementation does, and that overall slows down innovation. In the meantime, while standards are still in development, I think we need more open source software to step in and help fill this gap. And the first reason why open source development is especially important for confidential AI is just the accessibility. Because building distributed confidential computing tools for completely heterogeneous infrastructure is going to be really hard. Thousands of organizations want to build AI applications that need these security guarantees, but like vanishingly few actually have the skills to implement them, because you need people who deeply understand cryptography, systems design, and hardware security all at once. So very rare combination. With a few open source projects with teams with deep technical expertise can build foundations that others can at least learn from, if not integrate into their applications. This also helps with transparency, because peer review becomes like a validation process if formal validation doesn't exist. And finally, open source solutions are often designed for interoperability, helping to prevent vendor lock-in. One open source project I'll be following is the Certifier framework for confidential computing. And this project is coordinated by the Confidential Computing Consortium out of the Linux Foundation. They support a lot of interesting projects in this area. And I just highlight their quote from the README because I like their vision for interoperability, and that's very needed to actually serve a diversity of businesses and use cases. So just note that this project is open for contribution. So coming to a close, I'd just like to make a little call to action. There are people in this room who have the skills and knowledge to shape AI security for the better. And I hope that with your involvement, we'll see work towards open standards that everyone can innovate on, tools that make confidential applications accessible to more developers, and just more positive applications of AI in sectors where trust and compliance currently block progress, like healthcare and government especially. So I already talked about getting involved in open source, but you can also engage with standards bodies. For example, NIST releases public comment processes whenever they're developing or updating a standard. There are third-party review programs where hardware vendors themselves will submit additional details of their implementation for external review by security experts. And finally, try to bridge AI and security communities, for example, by going to some of the AI sessions here at USENIX Security. So if you're interested in contributing to confidential computing and don't know where to start, feel free to come talk to me, and I can point you to organizations and people who are actively building in this area. With that, thank you very much for your attention, and to the organizing committee for putting this session on. And yeah, please feel free to reach out if you'd like to discuss any of this. Thank you.